All right, cool. How's everybody doing? Good. Awesome. So last time we discussed for the first time multivariable systems. So these are systems in which you have perhaps many interconnected subsystems. These are very common in civil engineering, where we're typically dealing with kind of large networks, maybe a truss network, a water distribution network, traffic network. So most of the systems we'll be dealing with in civil engineering are going to be multivariable systems. We showed how we could construct multivariable systems for a somewhat familiar problem. We looked at a two-tank system in which the flow into the second tank depends on the state in the first tank. We showed how we could express it in matrix form like so. Okay, so we have our elements here. We have a state vector, which describes the states of the system. We have some inputs. So this is the input that is driving the system from outside. We have a system matrix, which describes the dynamics of the system. So it describes the homogeneous dynamics of the system. And we also have an input matrix, okay, which describes how the input enters the system. And altogether, this equation is sometimes called the state space form. We also talked about observation equations. Can anyone in their own words kind of describe what the observation equation does or is? So we looked at an example where we had, one sensor that's able to read the state of only the second tank. And we showed how we could express our observation of the system, what we're able to observe in terms of a second equation called the observation equation. In this case, we had that y was equal to 0, 1 times h1, h2, and there was no other component. So the observation equation allows us to express what we are able to observe about the system. Okay, and it's going to come in handy when we start getting into estimation later in the course, when we don't have access to all of the states of the system directly. We may only be able to observe a subset of states, but we can still use some mathematical techniques to infer what the other states of the system are. Okay, so we talked about how we could apply this state space form to describe a system consisting of two interconnected parts. We also discussed how we could use the state space form to describe higher order systems in a different way than we've been doing before. So we had our structural system. It had some stiffness, some damping, some mass, some forced input, which induces a displacement, as we are familiar with at this point. We know the expression for the dynamics of the system in single variable form. We showed how we could convert it to a state space equation by redefining our state variables such that we separated out our system into two first order equations, two first order differential equations. So we set x1 equal to x, the displacement, and x2 equal to x dot, the velocity. And in this way, we were able to express our original system in state space form. Okay, and this is going to be useful later on if we want to express the dynamics of higher order systems or coupled higher order systems together. So perhaps, a structure consisting of multiple elements that are interconnected, a multiple story structure or a truss system and so on. Okay, are there any questions on the state space form as introduced in the previous lecture? Anything that's still unclear on how we formulate these systems or why? Okay. All right. Very good. So we introduced this state space form. We're going to show a little bit later on in the class how this is going to be really useful for solving control and estimation problems. Estimation in particular is one thing we haven't looked at yet, but we really need this form to think about, to reason about those problems. So before we can really get into more advanced techniques for modeling estimation or control, we need to take a sidetrack into the land of linear algebra. Okay, so before we can really start analyzing these systems further, we need to kind of review some linear algebra concepts, introduce some new concepts, and then show how those concepts inform our understanding of dynamical systems in particular. Okay, so we are going to move into linear algebra. Today, what I'm going to do is just give an overview of linear algebra for those of you who maybe haven't seen linear algebra in a while. Okay. So first of all, who has used linear algebra so far in your graduate studies? Okay, a couple of you. Okay. For those of you who haven't, when's the last time you used linear algebra? So, it's been a while. I know when I started in grad school, I hadn't looked at linear algebra for many years. And so a lot of the concepts were still rusty for me. And in some sense, I also just didn't fundamentally understand some things in linear algebra because they weren't introduced very well at the undergraduate level. So we're going to take a very detailed journey through linear algebra, both the theory and applications. You're going to understand what matrices actually are, what vectors actually are, what linear transformations are actually doing. And so by the end of this module, which will take a couple of weeks, you should have a strong graduate foundation in linear algebra. So we'll get into the theory side next week. Today, we're just going to be looking at the mechanics of linear algebra. So looking at vectors, matrices, how do you multiply a matrix and a vector together? How do you multiply two matrices together, and what's actually happening when you do that? Okay, so today we are going to take a geometric review of linear algebra. Okay, and we're going to just focus on the mechanics and definitions. We'll start to get into the theory and intuition next week. Okay. So first, before we move on, let's talk a little bit about vectors. Okay. So a vector, we'll get into the formal definition of what a vector is next week. But for now, you can think of a vector as an ordered collection of numbers. So I'll say vectors are ordered collections of numbers. Okay. Okay, so they're ordered collections of numbers. The number of elements in the vector is its dimensionality or dimension. Okay, so I just want to give you some terminology. Okay, and so by convention, we're going to assume for this class that all vectors are column vectors. Okay, so if we have a vector v, it will be a column vector consisting of elements v1, v2, v3, all the way through vn. Okay, so each of these v's inside of the vector, this is a scalar. So v1, v2, v3, these are scalars. When I write a vector, in this class, I will underline it to indicate that it's a vector. Okay, so scalars will be not underlined, vectors will be underlined. Okay, and by convention, we're going to assume that all vectors are column vectors, so they are arranged vertically. So I talked about the elements inside the vector. So if these elements are real valued, okay, we'll say that our vector v is in Rn. So who remembers what Rn means? from last class? Yes, so Rn refers to the set of real valued n-dimensional vectors. So when we say V is in Rn, it means that our vector V is in that set. Okay, but that is correct. If complex valued, we may say that V is in Cn, so the set of complex valued vectors of length n. Okay. And if we want to talk about row vectors, I will denote them in this class by taking the transpose of an existing vector. So if I want to talk about a row vector, one that is arranged horizontally, I will say V transpose, okay, where you have elements V1, V2, V3, all the way through Vn. Okay, so by convention, I will be using column vectors in this class. Other fields may have different conventions. Okay. Are there any questions on this definition? Well, this isn't really a definition, but this is kind of just an intuitive sense of what I mean when I talk about vectors. So vectors are ordered collections of numbers. What are some examples of things that can be represented by vectors? Maybe from your experience doing research, your experience in other classes. What are some examples? What are some examples of vectors, or what vectors can be used for? Exactly. So that's one of the most common uses for vectors would be spatial coordinates. And this can be in 1, 2, 3, all the way through n-dimensional space. So very good. So that's one of the most common uses for vectors. What are some other examples of what we can use vectors for? Sorry? Sorry, can you say that again? Settling velocities. Okay. So is that something that you use vectors for in your research? Oh, okay. So yeah, so you could use vectors to represent settling velocities. As we showed in the previous class, we can use vectors to represent our states of a dynamical system. So if we have states of a system that are connected in some way, we can represent these states of dynamical systems. So one of those states might be the settling velocity in a tank. Okay. It could be the position and velocity of a structure, right? We can use vectors to represent our states. What are some other things we can use vectors for? Sorry? Yeah, so that might be another example of states in dynamical systems. Here's one example that you might see in the domain of machine learning, images. So you can, if you have an image, it consists of a big grid of pixels, right? You might have an image that's a big grid of pixels. So common practice in machine learning, for example, is to take this image and unravel it into a single long vector. And this is often one of the pre-processing steps before you train a neural network, for example. You may take an image that's a grid of pixels and just unravel it into a single vector where each element of the vector refers to, for example, the intensity of the pixel in grayscale or something like that. Okay, so it's often used to represent images. Another use for vectors that you'll find in the domain of signal processing, time series data. So let's say maybe you are taking samples of water quality. You're taking some samples over time. You may have a sample taken at time 1, so this is some concentration, a sample taken at time 2, a sample taken at time 3, all the way to sample taken at time, I'll just call it t. And you can stack those together into a vector. Okay, and this is an important pre-processing step as well in many signal and image processing algorithms, is that you want to represent that time series data as a vector. What are some other examples maybe you can think of for what vectors can be used for?
In natural language processing, each word can be represented as a vector.
Right. So natural language processing, many machine learning algorithms are heavily dependent on linear algebra and vectors. So this class will give you a good foundation, if you haven't already gotten one, in how you can formulate data into vectors and use linear algebra operations to reason about it. Okay. Any other examples you want to volunteer for vectors? Okay. One other example we'll be looking at in this class. So when we get into what vector spaces are, or polynomials. So we can represent polynomials as a vector with a series of coefficients corresponding to the coefficients on each of the terms of the polynomial. And you can even use linear algebra techniques, with the polynomial defined in that way to find the roots of the polynomial, which we might have some examples on later. But you can use vectors to represent polynomials or other essentially linear systems. Okay, so those are just some examples of vectors. Oops. Okay, yep, that's what I want to do. So when we're talking about vectors, there's fundamentally two operations that we can apply to vectors. There's two operations we can apply that take us from one vector to another vector. And those operations are scalar multiplication and vector addition. So let's go through each of these. It's going to seem like we're going a little bit slow at first, but I want to make sure everyone is on the same page when it comes to kind of our basic linear algebra concepts that we're going to be using. Okay, so when we have vectors, there's primarily two operations we can apply to them that map us from one vector to another vector. Those operations are scalar multiplication and vector addition. Okay, so let's talk about scalar multiplication. And this should be somewhat familiar from undergraduate. So a scalar multiplication essentially stretches a vector, which I'll call V1, by a scaling factor, which I'll call alpha, to produce a new vector V2. Okay, so we have that V2. Let me underline these just to indicate that they're vectors. V2 is equal to alpha times V1. Okay, so pretty simple. Let's go through a quick example of that concept. Okay, let's say we have V1, our vector is equal to the ordered collection 4, 2. And we have some scaling factor alpha is equal to 1/2. Let's go and visualize that. Okay, so we have a 2-coordinate system. Let's call this x coordinate x1, y coordinate x2. Let's add some tick marks. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Okay. And we have some vector V1, which is at 4, 2. So we go 4 over to the right and 2 up. And that's how we can represent our vector v1. Okay. If we are computing v2 is equal to alpha v1, then we simply take 1/2 times 4, 2 is equal to 2, 1. Okay, so this is very, very basic stuff, I know, but I want to make sure these concepts are clear. Okay, so we can draw that on our coordinate plane. We essentially just shrink our vector v1 by half. Okay, and that takes us to 2, 1. Okay, this is v2. Note that we can also, our scaling factor can also be negative. And what would that do in this case? Let's say we have a new scaling factor, beta is equal to -1/2. Okay, so where would our ultimate vector land up? Where would our vector land on the coordinate plane? Yeah, so we would have v3. V3 is equal to -2, -1. And so our vector would end up down here. Okay, so great. So this is review, hopefully. So we have scalar multiplication. Our other operation is vector addition. Okay. And in vector addition, we're essentially just adding 2 vectors together element-wise. Okay. So we add a vector v1 and v2 together to produce a new vector v3. Okay, so for example, we have that v1 is equal to 4, 2 as before. We have that v2 is equal to -1, 2. And so v3, if we add those two together, this should be v3. v3 is equal to v1 plus v2, which will be equal to 4, 2 plus -1, 2 is equal to 3, 4, right? Okay, and we can draw this out on the coordinate plane as before, just to visualize what's going on. Let me redraw that. Okay, so we have our tick marks here, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. All right. And again, I know this is a bit slow, so just be patient as we kind of cover these basics. I want to make sure these are clear before we move on. Okay, so our vector v1 is you go over 4 and up 2. So this is v1. Our vector v2 is at -1, 2. This is v2. And to get v3, we just add the components of v2 to v1. So we can go over to the end of v1 and add on v2. So if we go over to the left 1 and up 2, we will end up at 3, 4. Conversely, we can add the components of v1 to v2, and that will take us to the same place right here. So our vector v3, you just add them tip to tail. Okay, and that's 3, 3, 4. Okay, there we go. Okay, so pretty basic stuff, but very important. These are the 2 operations that you can apply to vectors. These are essentially what define what a vector and a linear algebra is, okay, as we'll talk about starting next week. Okay, are there any questions on vector addition or scalar multiplication? Okay. So I'm going to move on and review different products, matrix vector products, vector vector products, matrix matrix products. This is going to be important for your entire life, but especially for this class. Okay, let's take a look at vector products. There's two that I want to talk about in this class. The first is the inner product, and the second is the outer product. Okay, so for the following definitions, we're going to let X be a vector in Rn, Y be a vector in Rn as well. Okay, so for the inner product, the inner product of two vectors is defined as follows. So we can write our inner product as follows. We have this triangular bracket, X, Y. Okay. And the inner product is defined as follows. It's equal to X transpose times Y, or this is the dot product. Okay. And what this gives us is we take the elements of X1, so X1, X2, all the way through Xn. And we multiply them by the elements of Y, so Y1, Y2, all the way through Yn. So this will be equal to X1, Y1 plus X2, Y2, and so on, all the way to Xn, Yn. Or written more succinctly, we might have the sum from I equals 1 to n of xi, yi. Okay. So when you're taking the inner product, you're essentially going through each of those elements pairwise, multiplying them together, and then adding them up. And this is probably the most fundamental linear algebra operation we're going to do aside from scalar multiplication and vector addition. Okay, so let's go through a quick example.
If X is actually a row vector and Y is a column vector,
So they do have to be dimensionally compatible. So again, so this is for X in Rn, Y in Rn, with both of these being column vectors. So X and Y are both column vectors. So yes, this they do have to be dimensionally compatible. Okay, good question. Okay, so let's go through a quick example. You've probably seen this before. So let's say we have vectors -1, 3, 2. And our Y vector is 0, 4, 5. Okay, so if you take the inner product, or the dot product in this case, you'll get -1 times 0 plus 3 times 4 plus 2 times 5. Okay, and this will give you 0 plus 12 plus 10, which is equal to 22. Okay, so that's the dot product of two vectors, and note they do have to have the same dimension for this to work. Right, let's take a look at outer products. Who's heard of the term outer product before? Okay, anyone else heard of the term outer product? So this is actually going to be very important. Okay, the outer product, we have two vectors, X and Y. The outer product is defined as X, Y transpose. Okay, so note this is not the same as X transpose Y. Okay, so the outer product is equal to XY transpose. So X, our vector, will be X1, x2 all the way through xn. Our vector y will be y1, y2, all the way through yn. Okay, and if we're computing the outer product, what essentially is going to happen is we're going to take this vector x here, and we're going to scale it by each one of these y's and then stack them together horizontally. So I'll show you what I mean by that. So this will end up being y1 times x in the first column, y2 times x in the second column, all the way through yn times x in the final column. All right. And if you carry out that multiplication, what you should end up with something is with something like x1, y1 in the first element. Sorry, was there a question? X1, y2 in the second element, all the way through x1, yn, the final element of the first row. And this pattern continues downwards. So in the final row, first column, you'll have xn, xn, y1. Okay, and then the final element on the final row, final column, you'll have xn, yn. Okay. So note that in the case of the outer product, these don't need to have the same dimension. We'll talk about the dimensions for multiplication a little bit later, but they don't necessarily need to have the same dimension for outer product. Okay, so let's go through a quick example. I think this one is helpful to look at with a concrete example. So we're going to take our same two vectors from before. We have x is equal to -1, 3, 2, and y transpose is equal to 0, 4, 5. Okay, the outer product will be equal to, if we go through, so we'll take first this 0 multiplied by all of x1, all of x. So we'll have, we can write it out as 0 times -1, 3, 2. Here we'll have 4 times -1, 3, 2. And here we'll have 5 times -1, 3, 2. And we stack them all together horizontally. And what we get is, first row will be all zeros, 0, 0, 0. This row will be -4, 12, 8. And this row here will be -5, 15, 10. Okay, so that is the outer product. Who's seen the outer product before anywhere? Okay, so just a couple of you. Okay, so this is going to be really important. In fact, when we get to the next section, we're going to start talking about matrix vector products, matrix products. Let's just go into it. Let's start with matrix vector products. It's really hard to overstate how important what I'm about to show you is, if you haven't seen it before. In particular, I'm going to teach you two different ways to think about matrix vector multiplication and matrix multiplication. In undergraduate, probably you were only taught one of these ways, but actually understanding both of these different ways of thinking about matrix vector products and matrix products is going to be extremely useful. So this may be the most important thing I teach you in this class if you have not already seen it, okay? Hope I'm not hyping it up too much here, but this is an extremely important concept for just thinking about linear algebra. Okay, so I'm going to teach you two ways to think about matrix vector products. Okay, there's two ways to think about matrix vector products. The first is, well, let me just go into each of them. Okay, so let's say we have A is a matrix in R M by N, so Mike by November, and X is a vector in Rn. Okay, so there are two ways to think about matrix vector products. And to be clear, what we're talking about is A times X. That's what we're talking about when I mean matrix vector products. Let's just say this is AX is equal to B or something like that. Okay, we're talking about this product here. Okay, there's two ways to think about it. The first, which is the method that you probably learned in undergraduate, is a vector of inner products of X with the rows of A. Before I get into this, let me do a quick aside, just on notation. So I'm going to insert a little note here. So as an aside, when we're talking about vectors and matrices, it's sometimes helpful to use colon notation. So this is the same notation used by MATLAB and Python. Let's say we have A as a matrix in our M by N, Mike by November. Okay, we can denote A colon comma J as the jth column, of A. And we can denote A I comma colon as the ith column of A. So for instance, if we have A, we can write it as either a series of columns like so. So we have A colon comma 1, A colon comma 2, all the way through A colon comma N as in November. We can also write this as its rows. So this would be, sorry, this should be A transpose, because when I talk about rows, I will refer to them as the transpose vector. So this will be A1 colon transpose, A2 comma transpose, and so on all the way to AM colon transpose. This is just a notational convention that we'll be using to describe matrices, okay? Yeah, these are the rows of A. Yes. So that's just how we'll be expressing them. So these are both the same matrix. It's just this is writing it in terms of its columns. So it'll be A colon comma 1, A colon comma 2, all the way through A colon comma N. We can also write it in terms of its rows as follows. Okay, sorry. Yeah, this should be is the ith row. Yes, sorry about that. Okay, so this is a notation that we'll be using. Okay, so let's get back into it. There's two ways we can think about a matrix vector product. The first is the vector of inner products of X with the rows of A. So this is the way you were probably taught in undergraduate. So let's say we have AX. This is equal to, if we think about it in terms of the rows, we have A1 colon transpose, A2 colon transpose, all the way through AM as in Mike, colon transpose. Okay, and we're taking these rows and we're multiplying it by some vector X. We're taking each of these rows and we're multiplying it by a vector X. Okay, so what we'll end up with is a vector of inner products where each element is the inner product of a row of A with X. Okay, so we may have a vector of inner products here. We have A1 colon T inner product with X, A2 colon T inner product with X, all the way down to A M colon T inner product with X. Okay, so this is the way you're probably taught to perform matrix vector products in your head. let's go through an example of how it's typically done with a couple of real numbers in there. Okay, so let's say we have a matrix A, which is 2, 1, 0, 4, 3, 2. Okay, and we're going to multiply it by a vector X, which is 1, 0, 3. Okay, so for the first row of our output, we have 2 times 1 plus 1 times 0 plus 0 times 3. So we took the inner product of this first row with our vector X. And in the second row of our output, we'll take the inner product of this second row with X. Okay, so we'll have 4 times 1 plus 3 times 0 plus 2 times 3. Okay, and if we perform this calculation, we will get an answer 210. Okay, so who's seen this way of doing matrix vector products before? Probably all of you have seen doing it this way. There's another way to think of matrix vector products, which is perhaps the more fundamental way in terms of the actual definition of vectors. And that is, we can think of a matrix vector product as the sum of the columns of A scaled by the elements of X. Okay, so we have some matrix vector product AX. Okay, this will be equal to, so we'll think about A now in terms of its columns. So we have A colon comma 1. It's our first column, A colon comma 2, all the way through A colon comma N as in November, multiplied by the elements of X. Okay, so we'll think about our vector X now in terms of its individual scalar elements. So X1, X2, all the way through Xn. Okay, and so what we're going to think about now is if we take each one of these columns here, we're going to scale it by the elements of X and we're going to add them together. Okay, so we will have X1 times our vector A colon comma 1 plus X2 times our vector A colon comma 2. And so on, all the way to Xn times our final column of A colon comma N. Okay. And we can write this succinctly as a sum from I equals 1 through N of Xi with A colon comma I. Okay, who's seen this way of doing matrix vector products before? Okay, we have. Has anyone else seen this method of doing matrix vector products? Okay, a couple of you. Okay, so this is, again, it's really hard to overstate how important this is for thinking about linear algebra. I want you to really get comfortable with thinking about it both ways. Okay, so let's do an example. It turns out that both of these definitions are the same. If you look underneath. Okay, so let's go with the same vectors we had, same matrix and vector we had before. So we have 2, 1, 0, 4, 3, 2. And our vector is 1, 0, 3. Okay, so what we're going to do is we're going to go through each of these columns. So we're going to take our first column here. We are going to multiply it by 1. Then we are going to add that to our second column multiplied by 0. And we're going to add that to our third column multiplied by 3. So we have 1 times 2, 4 plus 0 times 1, 3 plus 3 times 0, 2. Okay, if we add these together, we will get 2, 4 plus 0, 0 plus 0, 6. And if we add these together, we get 210, which is the same answer we got before. Okay, so these are two different ways of doing the same thing. I want you to get comfortable with both of these, okay? Okay, on a related note, we can now come up with two different ways of expressing matrix multiplication. Okay, so there's two ways to think about matrix multiplication. Okay. Let's say we have A in R M by N, Mike by November, and B in R N by P, November by pineapple. Okay, so there's two ways to think about matrix multiplication. And to be clear, we are talking about C is equal to A times B. There's two ways to think about this operation. The first way, again, is the way that you were probably taught to think about matrix multiplication in undergrad. So that is as a matrix of inner products. Okay, so let's say we have AB. We're going to think about this in terms of the rows of A multiplied by the columns of B. Okay, so we're going to take the inner product of the rows of A with the columns of B. This is probably the way you were taught to perform this by hand. Okay, so we'll have A is equal to A1 comma colon transpose all the way through A M as in Mike colon transpose. Okay, we're going to think about B in terms of the columns. So B is going to be B colon comma 1 all the way through B colon comma P. Yes, P. Okay. And what we're going to do is we're essentially going to take the inner product of each of these rows with each of these columns. Okay, so the first element in the upper left-hand corner will be A1 comma colon inner product with, actually, I don't need to write the transpose because I'm writing in the triangular bracket form. So it'll be A1, actually, I'll just keep the transpose in there. Okay. B colon comma 1. Okay, all the way, if you go down, you'll end up with A M comma colon transpose inner product with B colon comma 1. So the final row of A inner product with the first column of B. And you can extend this pattern. We'll do an example to make it more clear. In the upper right-hand corner, we'll have A 1 comma colon transpose inner product with B colon comma P. And if you go down, you will end up with A M colon inner product with B colon comma P. All right, so let's do an example to make this more clear. Again, this is the way you were probably taught to do it in undergrad. Okay, so let's say we have A is equal to 2, 1, 0, negative 3, 2, 4. Our B is equal to negative 2, 6, negative 1, 5, 0, 3. Okay, so what we're going to do is we're going to go through. We're going to take this row of A, take the inner product with the first column of B, then we're going to take the first row of A, inner product with the second column of B, and do that for each combination here. Okay, so what we'll end up with is AB. Okay, so first we're going to take this first row of A, inner product with the first row of B, or sorry, first column of B. We'll get 2 times negative 2 plus 1 times negative 1 plus 0 times 0. So that'll be our first element. Second, for this upper right corner here, we'll have 2 times 6 plus 1 times 5. plus 0 times 3. Okay, so that's the inner product of this first row of A with the second column of B. Okay, on the bottom left corner, we'll have -3 times -2 plus 2 times -1 plus 4 times 0. And the bottom right corner will have -3 times 6 plus 2 times 5 plus 4 times 3. Oops, ran out of space. Okay, that's not very legible, but fortunately I ran out of space over there. Okay, so if you carry out all of those inner products, what you'll ultimately end up with is -5, 17, 4, 4. Okay, so this is probably the way you were taught to perform matrix multiplication in undergrad. There's another way to perform matrix multiplication, and that's probably going to be the way that's more important for this class. It's going to be extremely important when we get into decompositions and when we start talking about eigendecompositions in particular. So instead of thinking of a matrix multiplication as a series of inner products, you can also think of matrix multiplication as the sum of outer products. In particular, if we have AB, we can think about it in terms of the columns of A and the rows of B. Okay, so we have that our first column of A is A colon comma 1, all the way through A colon comma N, it's in November. And we can think of our B matrix in terms of its rows. So we'll have B 1 comma colon transpose, B 2 comma colon transpose all the way through B N comma colon transpose. Let me check the dimensions really quick. Yeah, it has to be N. Yeah. Okay, so we can take the columns of A, the rows of B, and we can define matrix multiplication as being the sum of outer products of the columns of A with the rows of B. Okay, so we can define AB as being equal to the sum from I equals 1 through N of A colon comma I. It's kind of hard to differentiate. I'll make it clear that this is a colon here. A colon comma I with B I comma colon transpose. Okay, so who's seen this definition of matrix multiplication before? Okay. Anybody else? Has anyone else seen matrix multiplication defined this way? Okay, again, this is probably the most important thing that I'm going to teach you in this class if you haven't seen it already. It makes it so much easier to think about some linear algebra problems. So I want you to get really comfortable with doing this. And in fact, I'm going to give you an example for you to work on yourself after I give you an example here. Okay, so let's take a look at a quick example. So we have the same A and B matrix from before. We have A is equal to 2, 1, 0, -3, 2, 4. We have B is equal to -2, 6, -1, 5, and 0, 3. Okay, so AB, again, we can define as the sum of these outer products. So we'll take the first column of A, the first row of B, and we're going to take their outer product. So we will have 2, -3, outer product with -2, 6. Okay, then we're going to take the second column of A, take the outer product with the second row of B. So that's going to be 1, 2, outer product with -1, 5. And we're going to add that to 0, 4, outer product with 0, 3. Okay. If we carry out this computation, we should get -4, 12, 6, -18. Plus, so each of these yields a matrix, so 2 by 2 matrix. -1, -2, 5, 10. And this final one will be 0, 0, 0, 12. Okay, if we take these and we add them together, we get -5, 17, 4, 4. Okay, so it yields the same answer as before. I want you to get comfortable doing both of these. When I give you homework 5, you're going to get a chance to try both of these methods. Yeah, and the second form of this matrix multiplication definition is going to help a lot for certain proofs and for thinking about decompositions in particular. So SVD, singular value decomposition, and eigendecomposition are the two main ones. Okay, are there any questions on these definitions of matrix multiplication? Okay, I want to make a quick note about dimensions. Sorry?
Here we are multiplying the column with the column of the first A with the row of the B.
Mm-hmm.
We can't reverse this. Can we do the row of the A to the column of B?
As an outer product? Well, then you would have 2, 1, 0, which is a row vector, outer producted with the first column of B, but that would just be an inner product, right?
What we do that we just multiply the row of A with the column of B. With the row, we multiply with the both the column of B, the first column,
Mm-hmm.
then again with the second column. So it's like 2 by 2. And then again the row, we multiply with the column of B.
I might have to see it. Yeah, I might have to see the exact way you did it. But yeah, after class, if you want to show me, I'll take a look at that. I just want to make a quick note about dimensions, and then I actually want to give you 5 minutes to do one of these yourself. So a quick note on dimensions. So let's say we have A multiplied by B is equal to C. Okay, and we have that A is in R M by N, Mike by November. B is in R N by P. Okay, so we know that A is in M by N, B is in N by P. So in order to carry out matrix multiplication using the definitions that we gave, the inner dimensions here have to match. So these two need to be the same. So I'll say must match. And the dimensions of our output are defined by this outer pair. Okay, so in this case, our output will be M by P. Okay, so you take essentially the dimension on the left for A, it becomes the left dimension for C, so the number of rows, and the number of columns of B determines the number of columns of C. Okay, so that's something to remember when you're carrying out matrix multiplication. Okay, so what I want to do for the remaining time that we have, I want to give you an example, and I want you to go through computing this using both methods. Okay, so I'm going to give you an example. I'm going to set A equal to 5, 0, 1, 3, 4, 0. I'm going to let B equal 0, 1, 2, 1. And I want you to compute AB using the first method. And I want you to compute AB using the second method. I'll give you about 5 minutes to do that, okay? I think after that, that's probably all we have time for, but I will come and check on you after you finish this exercise. And go ahead and do this with a partner. if you have a partner you can do this problem with. Okay. Just to very quickly recap, I'll just do it the first way and the second way here. So the answer you should get, actually, I'm not going to have time here, but the answer you should get both ways should be 0, 5, 6, 4, 0, 4. Okay, so on Thursday, I will pick up where I left off. I'm going to have to cover a little bit more on kind of basic linear algebra review, and then I'm going to start getting into more of the theory side when we start talking about vector spaces. Okay, so that will be on Tuesday. Have a great weekend, and yeah, I will see you next week.